Hi, and welcome to our presentation for our Pokemon Drawing Deep Learning Network. My name is Guseppi Ragusa. I am here with my other team members, Arsalan Farooqui and Andrew Cobb.
Our goal when we created this application is to have a deep learning network that can predict the Pokemon that a user would draw and guess whether or not it's correct or not, based on a predetermined database of Pokemon already in the system. Our program asks the user to draw a specific Pokemon, and once that drawing is complete, the network will attempt to predict which Pokemon is drawn based on information. Whether the network is correct or not, the drawing corresponding label will be learned by the network for further improvement. Let's start with a demo of our application. So we'll run the file and it'll prompt us that it's using a TensorFlow backend. And now the application opens up and it says that you have to draw a Charmander, and it gives you like a little picture. It then opens up Paint on the user's computer, and it opens up a 255 by 255 blank canvas, and the user is now asked to draw that Pokemon. In this case, a Charmander. Cute little lizard with a tail on fire. While we're drawing, let's use this as an opportunity to explain what's going on behind the scenes of our neural network.
So our network uses a backend known as TensorFlow. This is a high-level API that contains a variety of tools and libraries used to build advanced deep learning networks. One of these libraries is a Python library known as Keras. Keras contains all the necessary functions and objects that we needed to build our network.
Our Charmander is coming along quite nicely. Very, very shapely legs, a little bit terrifying. 1,000-yard stare, cute little tail, and a bit of fire. And now that the user's done drawing, they press save and they close the app, and the application now uses that picture to make a prediction. And in this case, it predicted that it was a Charmander, which is correct. And let's try drawing again. Let's see what happens. So now same thing. Application gives us a prompt saying to draw this Pokemon. And in this case, it's a Squirtle. And now we have to draw a Squirtle. Beady little head with beady little eyes. Cute little water Pokemon turtle. He's a little bit very round, but that's okay. He's been eating a lot. He's a bit of a fat boy. With unusually stubby arms. Just as a reminder, we're programmers, not artists. We're trying our best. And now our cute little tail. We can't forget that. So let's press save, close it, and let's see what the model says. And the model is correct again. It correctly predicted that it was a Squirtle. So let's press no, and let's see what happens. So now, the model is compiling all this new data and going to the k-fold process to train itself. Just slowly going through. And now that it's done, it actually spits out our current accuracy. So overall, roughly a bit over half the time, the model will correctly predict what you drew. And it'll spit out a graph of our previous attempts at drawing. And as you notice, there's sort of a trend where we have like our peaks and throws, but gradually the accuracy of our model is slowly going up. And that should be it for our demo.
During our demo, you may have heard Arsalan mention something known as k-folding. This is a process that we are using for our neural network to help increase its accuracy. An accuracy of 57, while decent, is not as high as we would want for our network. While a simple way to fix this would be to give it more training data, we do not have this. Therefore, k-folding is the next best option. On the left side of the screen, you will see the code that is required for our k-folding process. K-folding is the process of taking all of the training data and evaluation data and splitting it into equal sections of smaller sizes. In this case, we have chosen 5. We have created a loop that will iterate through each section of the training data and evaluation data, and the model will take each one of these sections of data and run the network on it. While the accuracy will start out low at first, the benefit with k-folding is that each iteration will slowly increase the accuracy because it uses the accuracy of the previous loop and the previous data to help give more accurate results. Our application uses a special kind of network known as a convolution network, which is a network that specializes in recognizing images. Thanks to Keras, creating this model is quite simple. You will notice for our model we have used multiple layers known as conv2D. This is basically a convolution layer. What this layer does is it uses a kernel to iterate over patches of pixels and finds the average of them. The reason why it does this is because this allows the network to recognize specific shapes and patterns or abstract objects within the picture. Another layer you'll see often is known as max pooling 2D. This performs an operation known as max pooling, which performs similar to a convolution network in that it uses a kernel to iterate over patches of pixels. But rather than finding the average, it instead finds the maximum. The reason for this is because this allows the network to see small details hidden inside certain parts of the picture and to emphasize them more so that the network can use that as evaluation data. These 2 layers are repeated multiple times because every time it does this, the patterns that the network can see become more visible. And this allows the network to evaluate its predictions more clearly. So the result of our convolution and max pooling layers is a 2D array of pixel values. The flattened layer highlighted takes this 2D array and turns it into a single layer or a single array. And the reason why we have to do this is because our next layer, the dense layer, cannot take a 2D array as an input. It needs a one-dimensional array. The purpose of the dense layer is to take all the patterns recognized by the convolution and the max pooling layers, and it turns it into patterns on a global scope. The convolution and max pooling layers only recognize patterns locally, therefore a dense layer is needed to turn these patterns into the global picture that we are trying to recognize. The last layer of the network is the output layer. We are using an activation known as softmax because the output that we are trying to give is one of multiple options. In this case, we have one of 5. Now that we've discussed our model and the layers of the model, it's time to compile the model. You'll notice that when we compile our model, we have an attribute called loss. This is our loss function, and this determines how well our model evaluates itself. The loss function we are using is known as categorical cross entropy, and we are using this because the output of our model is one of multiple categories. We are retrieving the accuracy metrics from the model for our sake so we can see how well the model is doing. In the create model function, this is where we actually run the model. Okay? Using the fit option of the model, we will input the training data and evaluation data that we have collected. Okay? The model will evaluate over this training data and evaluation data 8 times. This is what the epochs attribute represents. The reason why we've chosen 8 is because this is the balance between overfitting and underfitting for our model.
So let's go over how we made this project. This project really shows the magic of Python, as we're able to execute a fairly complex task, but every little step we do is really simple. So as you can see here, we have a mostly blank Python file. We have our two main imports, NumPy for dealing with data, and Keras as our wrapper for the TensorFlow machine learning library. I've also defined the Pokemon we're going to be drawing as a Python list. This allows them to be referenced by a numerical index, which just makes life easier later on. And below that, we got some basic Python code. I've defined an entry point for our application and a main function that's just going to keep the script running until the user presses N to quit. So for this project, we used an environment called Spider. Spider is an IDE that comes bundled with Anaconda Python. That's nice because it's going to be integrated with your installation of Anaconda right out of the box. You're going to be able to access your machine learning and data science libraries without need for any setup. You also have a Python terminal right here on the right for running and testing code. It's a really nice feature as it's set up to work with Anaconda, and as you saw in the demo, it can display graphs and images nicely in line, which is something I found difficult in other IDEs such as JetBrains or Visual Studio Code. But unlike other IDEs you may have used in this course, Spider works with ordinary .py files, as opposed to the Python notebook files used in Jupyter Notebooks or Google Colab. This gives you the advantage of ending up with a generic Python script that you could potentially make into part of a bigger application or even a website. It also just tends to work better as a standalone application. Before we get too far along, let's do a quick overview of our project directory structure. As you can see, we have 4 folders here with our Python script in the root directory. So our first folder is the data folder where we're going to be storing our binary files for persistent storage. Empty right now because we haven't run the application, but on the first run through it's going to save our neural network along with our data and history files. Next we have the image folder. Again, it's empty at the moment, but this is our temporary working directory where we're going to save and load the images that the user is going to be creating. We're just putting them in their own folder so they're out of the way of the rest of the application. Next we have the seeds folder. And here we have roughly 60 drawings of Pokemon that we got from our friends just so we have some data to start the convolutional network off with. As you can see, these are all human drawings, and everyone has their own idea of what to draw. Right, you got some people who made very detailed drawings. Got other people who put in less detail. We also have some people who drew pretty much exactly what they saw. Other people did a bit more creativity with posing or angling the Pokemon. This is what we wanted because we wanted a generic neural network that could recognize human drawings, not necessarily humans doing exactly the same thing all the time. So along with the drawings, we have our keys file. So this is a simple text document. It relates each picture of a Pokemon with the numerical code. So if you remember, we had that Python list that associated a number with the name of a Pokemon. So this is just associating each picture, right? So Pokemon 1 on line 1 has a numerical code of 1. Pokemon 2 is a numerical code of 0, right? And these relate to the name of the Pokemon in our list. So our final folder is the starter Pokemon folder. Here we have just the official drawings of Pokemon. These aren't actually part of the convolutional neural network. They're just here so that when we ask the user to draw a Pokemon, we can display a picture of that Pokemon, just in case someone doesn't know what Meowth or a Bulbasaur looks like. Okay, let's get to programming. Jumping right down here to the main loop. What do we want to do each loop? We want to play the game. So let's just define the function here. And here's what this function is going to do. First off, we're going to load the machine learning model. We're going to pick a random Pokemon. We're going to get the user's drawing of that Pokemon. We're going to make a prediction based on that drawing. We're going to check our prediction. And then finally, we're going to save that new data to our data set. So, okay, let's look at how we're going to do it. First, let's make a function to load the model. So our model will equal load model. Load model. So this function is going to do one of two things. If we have a model saved, we're going to load that. Otherwise, we'll create a new model. So to check if our model exists, we're going to need to import the OS library. So let's just import that. Import OS. We also want to define where that model is saved. So let's do that now using a global variable. Model file. So remember from earlier, we had that data directory for our saved data, and our model file is going to be saved as a .h5 exception. So we'll just call it model for now. .h5. Okay. Now we have our file name. Let's see if it's there. So under the load model, if so we use the path.isFile function. This is going to return true if it finds the file. The file we want to find is model file. Right. So if we can find that model, we can return it, and we'll just call this function here to load it using that same global variable. So return curious.model.load and our model file. So if we don't find the saved model, we're going to have to create a new model. So this would be if it's the first time the application is running and we have no saved persistent data. So right here, let's display a message to the user, tell them what we're doing, just using the print function. This is obviously a resource-heavy task, so we just want to let the user know that stuff is happening in the background. And now just to keep stuff organized, we're going to leave creating the model to another function as something we're going to do more than once. So let's just now return a new function called create model. Okay, creating the model. This function is not going to do a whole lot, but mostly just call other functions. So defining create model. First thing we're going to do is we're going to need some data, x and y. Pretty much like all machine learning models, we need our input data x, our output data y. And again, we'll just leave this to a get data function. Go and do that function later. For now, the next thing to do after getting data is to get the model definition. So our model will equal get model again. We'll just leave it up to a function. We'll get to that in a bit. And now we have the model and some data. We can fit the data to the model. So model.fit. We're fitting x and y. Epochs are going to be 8. That's a bit of an arbitrary decision, but I found this a good compromise between accuracy and overfitting and not too resource heavy. Next, batch size is equal to 64. That's system dependent. You're going to have to find a number that works for your hardware, but 64 seems to work well on this computer. And finally, verbose is equal to 0. So you might not have seen this verbose param before. All it does is it stops Keras from displaying a bunch of data to the console, just to keep the console a bit cleaner when we're running this as an application. So now that we've gone to the trouble of creating a model, we actually want to save it so we don't have to do this every time we run the application. So model.save, just using the inbuilt Keras function here, and we're saving to model file. And we can return here. So this save function is a bit like pickling. We're just keeping the binary data as a file, so the next time the application loads, we can load it quickly when needed. Again, just using that same global variable we defined up here. Okay, so next up, we want to get data. So let's define that function. So this is going to follow the same basic pattern as loading the module. We're going to check if the file exists. Otherwise, we're going to have to create some data from that seed folder that we saw earlier. Again, let's use global variables where we stored our files. So data x is equal to So we're using the .numpy extensions in that same data directory we used earlier. And now in our getData function, we're going to check if these files exist. os.path is file data x. Path is file. And same for data y. In theory, if x exists, we should have also created y at the same time, but just to be on the safe side, we're going to check for both of them. If either one of them don't exist, we're going to start again from seed data. So if they do exist, we can just load them. X is equal to numpy dot load, loading data X, and same for Y. Okay, and we just want to return them here. We'll return them as a tuple, so returning both X and Y in one go. Right, so if you remember, if we don't have X and Y, we had that seed folder where we had a bunch of pictures and a keys file. So right away, let's create a X variable that's going to hold our seed images. Sorry, fighting with the ID a bit here. And then Y, since this Y is just a text file, we can just load that directly into our array here. And it was seed slash keys dot text. So if you remember when we showed you this file, we had a row for each Pokemon drawing and a numerical representation of that Pokemon. So the index in this array here. But neural networks give out arrays as answers. They'll give out an array. Say if we wanted 3, it would give out an array 0, 0, 0, 1, 0, 0. So we need to transform our data to be in that that format. So fortunately, Keras has built in a function to do just that. And this is very similar to how you would go about it if you were loading in data into a Jupyter Notebook from the MNIST dataset or something. To categorical, and we give it Y, and there are 5 options it could be out of this list. So our next parameter is just 5. Okay, so now we can start loading our X data, our images. So each bitmap was just called Pokemon 1, Pokemon 2, etc. So we can easily load them in a loop. We can just use our Y parameter to figure out how many seeds we have to load. Just look at the shape of Y, and we want the, because it's now two-dimensional array, we just want to make sure we get the 0th axis. Okay, so now because I named the first drawing Pokemon 1 instead of Pokemon 0, we're going to have an off by 1 error. So our loop needs to look like for I in range. And if we just ranged seeds, would start at 0. So we want to start at 1, and we want to keep going to num seeds. So we go num seeds plus 1 there. And we can load our image. Image.open. Seed Pokemon. And we want the string value of I and an extension of BMP for bit. Right, so now we're using our image library here, so we're going to have to import that. So jumping back up to our imports here. From the PLI library, we're going to import image. Again, this is a fairly standard library for working with bitmap images. Okay, so now we have our image as a binary bitmap, but we want to use NumPy for our data, so let's call nparray to convert that bitmap image into a numerical NumPy array. So we can just do that in the same line here, np dot array. And then we're just going to append our x variable up here with our new image. So now we have all our images as a Python list. We've got a few things to do before we return them. First of all, let's transform them from a Python list to a NumPy array, again, just to make our lives easier. Now we're going to reshape them, because right now all the images are a 2D array, but Keras expects the color depth as a third dimension. So we're going to reshape them here. Reshape. We still want num seeds number of images. Each image is 255 by 255 pixels, and then we're going to have our final dimension there for the color depth, right? So now instead of it being a array with just a 2D array with just the color depth as a value, the color depth is now a dimension. We only need one here because they're black and white images, so we only have one value for color depth. And next up, we're just going to quickly normalize the data by dividing by 255 for 8. It takes our 8-bit color depth down to a number between 0 and 1, and that just helps if there's some dithering or anti-aliasing going on in the image, or someone just drew it with a slightly lighter color. Okay, so now we can just return x and y, again returning them as a tuple so we can return them both in one line. All right, let's get back to our create model function. The next thing we wanted to do was get model. So def get model. So I'm just going to be a bit lazy here and copy across our definition. So as you can see here, our model uses 3 convolutional layers, right? Here, here, and here, each followed by a max pooling. And then there's a single hidden layer that's actually going to create our predictions. So these super parameters, they're all a little bit of a guess. We don't really know what's going to work until we have a much larger data set to experiment with. So we can revisit these at a later date. These are just parameters that work for me, and I've seen them used in other people's work examples, and they just seem to be a fairly standard way of setting up an image recognition neural network. We'll probably want a dropout layer in here as the data gets larger, but for right now, that's just causing too much randomness in our model and hurting our accuracy, which is already pretty low because of the data set. Compiling our model, using categorical cross entropy, because obviously this is we're trying to categorize images, and accuracy is our metric. So we can now return our model. Right, so after all that, we can go back to our play function. And we are done with loading the model. So pick a random Pokemon. So we will call this new Pokemon. And it is just going to be equal to a random integer between 0 to 4, right, representing an index in our array up here. And we have another module to import because we want our random data. So from random import our random integer function. Okay, so now we need to get our user to draw the Pokemon. So again, we're just going to define a function. We want our input underscore image. Let's call it img is equal to and draw Pokemon. And we want to pass it our new Pokemon integer here. So let's go and define this. Def. And it is taking a y value. First off, let's just create an image file as a template. So we know we're going to get an image of the right size as opposed to letting the user pick a random image size and color depth. So template image is going to be image.new. And we're using that PLI image library from earlier. So first parameter is L. That signifies 8-bit black and white color depth. I'm not sure, honestly not sure why that's represented by L, but it is. 255 is our size, so 255. And we want to start off with a blank white image. Okay, let's save that template as an image. .save. And we'll use the img folder, which we saw earlier. .bmp. Now, let's load up a picture of the Pokemon we want to draw to show the user what he looks like. We'll just call it img for now. It's equal to image dot open. So we're opening an image from our starter Pokemon directory, and the image we want to look up is Pokemon at Y. So we're using our array up here to translate our numerical value for the Pokemon into a string value. And it's going to be saved as a bitmap, so just concatenate .bitmap, concatenate on the file type there. And we want it to change it into a NumPy array to make it easy for us to display. Because the easiest way to show images in Anaconda is to use the matplot library. So let's go grab that import. lib.py as plt. What were we? Draw Pokemon. So let's print a message here. And we'll turn our axes off to make the image look nice. And we'll give it a title. And we can use that Pokemon array, again, global variable, to get the name of our Pokemon from the numerical value. And plt.im show to show an image. And then finally we call plt.show to keep that image open up in the terminal. Okay, so let's open up MS Paint for the user, and we'll do that in a new function. Just call it open MS Paint, and then we can return our image.open, and we'll open up our new image, right, our blank template, but hopefully, since we've opened up MS Paint, the user is going to have opened that image and drawn us a nice Pokemon in there now. So because we're in a Windows environment, we're using MS Paint. If you're working in a Apple environment, this next bit of code you're going to have to change, obviously, but let's define our Open MS Paint. I'm just going to throw together a very quick command in this function. It's going to get passed to the Windows command line. Then MS Paint. And we'll just quickly define the directory that we're opening is our image directory. Our name we said was new image, so that currently blank template that we want them to put their drawing into. And image editor path, right? So this is just the path to where MS Paint is saved in a Windows environment. Just copy that down. Okay, and then we're going to use a editor string, so save as os.path, and we're going to join our directory variable with our name variable to get the path of our template image and our editor string. So we're just going to use the string builder here to quickly create a string that we can pass to the Windows command line. And %. editor path and our save as path, right? So it's just going to glue these two strings together in a format that's going to be recognized by the Windows command line. And we can just pass this string to the os.system, system spelled correctly, editor string. So this will hold the execution of our Python script until this command is resolved by the operating system. So that means for us in this case, because we're opening up an application, the command line will stop it until that application returns finished code. So it returns 0 if it's finished correctly or 1 if it crashes. For now, we're going to assume that the user will draw the Pokemon picture in the open version of Paint, save it, and then close Paint down. And that should actually be it for this function. So it's going to open Paint, it's going to freeze operation until the user's finished with Paint, and then the process will continue, and we'll be going back to draw Pokemon, and then we can reopen that same template image now with a new drawing inside it. So that takes us all the way back to our play function. So we have our input image coming in from the draw Pokemon function, but it's coming in again as a binary bitmap image. So immediately we want to call on NumPy array function to turn it into a NumPy array. And we're going to do the same reshaping. Just have the one image, 255 by 255, and a new dimension for color depth, exactly like we did when we were loading the seed images. And we're also going to normalize it. Just going to do all that really quickly in one line here. So now we can move on to making a prediction. Pokemon predict. Get our model. Predict, and we're making our prediction based on the input image. And because we're only making one prediction, we want to take that array and just get the first element out of it. And this is going to return an array of 5 length with a 1 representing the Pokemon that the neural network thinks you drew. But we want to take that and go back to a single numerical value representing our Pokemon, again representing the index in this array. So again, we can just use the built-in Keras libraries to quickly do that for us, or NumPy built-in libraries in this case. All right, and this is just going to give us our single value. Right, so let's show the user what they drew and what our neural network thinks they drew. So we're going to just quickly print out a message. And we'll use our matplotlib to show the image just like we did before. .imShow to show an image. And we want to reshape that image because while QRS likes to have all the color depths as separate dimensions, Matplotlib is designed to do 2D graphs, not 3D graphs, so we need to reshape it back down to a 255 by 255 two-dimensional image, and we will give it a color map of gray because these are black and white images. And now we can plt.show. Again, we call, because we're working in a console environment, plt.show will keep the image showing in the console as the code continues to execute, so that image doesn't disappear immediately. And we can tell it what our neural network thinks that Pokemon is. And we want to get the name of our Pokemon, so again we use that global variable. And we have our Pokemon predict as a variable, a single variable that we can put into as an index for that list. Okay, and now let's see if we were correct. So if our Pokemon prediction is equal to the new Pokemon that came from our random choice up here, we can brag a bit. I was correct because our neural network has worked. Else, if we're incorrect, clearly it is the user's fault, so we'll tell them they're not very good at drawing Pokemon. Okay. So save our data again for organization. We're just going to create a new function. We're going to have to save the input image. And we're going to have to save the numerical value of the Pokemon it's supposed to be. So that we can, if we got it right, we're saving the right answer. If we got it wrong, we're still saving the right answer. So let's go and define our save new Pokemon here. We have a new X data point and a new Y data point. And we want to make this data look exactly like the seed data we saved earlier. So our new Y, we want to turn it into a categorical array. So again, calling on the QRS utils. That's not right. Utils, not untils. Utils. To categorical. And we give it our new data point, and we still have 5 categories. Right, so we want to save this data, but we also want to save it along with all the data we previously had. So let's just quickly grab our X and Y from getData. We use that function, and we're going to append our new data to the previously saved data. Append. Appending X, our new X to X, and we're working on the 0th axis. And And same thing for y. Append y. And we're appending y as a list. New y as a list. And again, we're working on the 0th axes. And now we can just call on mp.save. This is a built-in function to NumPy just to create binary representation of NumPy data. We save to our data x folder that we defined earlier all the way up here. And we're saving x. And we can do the same thing with y. Okay, so I think that is our game loop done at last. But finally, let's jump down to the main function here. Before we exit, we want to do two things. First off, let's call our create model, right, just outside the main game loop here. Create model with a capital M. So this is going to recreate the model, but it's going to recreate the model with all those new data points we just saved. And last thing we want to do is evaluate our model. Right? So we can see that after we finish the game, how our model is improving over time. So let's just go and finally define that function. Right, so this might take some time depending on the system this is running at. So first thing we're going to do is just print a message telling the user what's going on. And we want to get our x and y values, again, using our get data function from earlier. And now to evaluate a model, we're going to use a method called k-fold evaluation, which you're probably familiar with. It's going to give us the best sort of approximate for accuracy for our neural network by using the complete data set through the various iterations. So let's just define our k-folds here. First parameter is our number of splits. Just go with 5, right? So that's going to give us 20% testing, 80% training, sorry, which is fairly standard. Random state we'll set to none for now. So because there shouldn't be a order to our data because we're drawing Pokemon in random orders to begin with, we're not going to do any shuffling. And we'll need to get the number of games, right? So we can show how we're improving versus the number of times people have played our games. So again, we can just use our y value of shape on the 0th axis. Will tell us how many pictures of Pokemon and how many answers we have. So let's also get a variable here to hold our accuracy for each iteration of the k-fold, and let's define our k-fold loop. First of all, let's define our, so for our train index test index in k-folds dot split, and we're splitting on the Rx dataset, X training and X testing equal X with our train index and X with our test index. Right, and we can just do the exact same thing again, but change it to Y. And we will need our model. So we'll just use the getModel function. Again, we can reuse all that effort we went to defining these functions is now paying off because we can just quickly reuse them here. And we're going to fit our training data to this new model. And we're going to use the same number of epochs as we did when creating the model. And batch size is still going to be the same, 64, again, somewhat system dependent. And we'll tell it to be quiet for now. And now we're going to use this k-fold accuracy list here to store the accuracy of this iteration of the k-fold loop. So just append it with our m.evaluate. And we're going to evaluate our test data. X test and Y test. And finally, we're going to delete our model. So this is just something I found helps with performance. Because the models obviously take up a lot of video RAM, if you just wait around for the Python garbage collector to come along and clean that up, you can actually run out of video memory when doing k-fold analysis. Again, depending on your system, you might not run into this problem. But if you call deletem, that's going to invoke the garbage collector to come along right away, clean up all your memory, tell it you no longer need this model, and then when you go into the next iteration, you're starting off with essentially a blank slate and all your system resources free to calculate that k-fold. So after doing all the k-fold, we want to get our overall accuracy. So that's just going to be the average or the mean of our k-fold accuracy list. And we will print that accuracy out for the user to see. Current accuracy is, and print out our accuracy. So now we want to grab our history so we can create a graph showing the history of this application, number of games versus accuracy. So it's going to be a NumPy array of the number of games we've played and our accuracy. Okay, so again, we want to view this against previous games. So our previous games are going to be saved in a history file. So let's go and create our history file again using our global variables, just like we did for data X, data Y. And our model, we're going to create a history. And it's just going to be another NumPy array saved onto our hard drive as a NumPy file. Okay, so we can say that we have the history for this session. Let's now get the history of previous sessions using pretty much the same pattern we've used to get our history for our X and Y data and our model. We're going to call on our os.path.is file to check if we have any saved data to access. And we're looking for our history file. And if we find it, we can just get our call numpy.load to save it to our history object and append our most recent game to our saved data. And we can just go num gains and accuracy. Right. So now that we have all our history data, it'll either just be our current data for this session if it was the first time we were using this game, or if we had a history file saved from previous sessions, it will load it up and append that data here. We want to get that data and put it into a format that we can plot. So we want two lists, one for our accuracy, which is just going to be the use array splicing to get one dimension of our history array, and the other dimension is going to be the number of games played. Oops, what am I doing? On the 0th dimension. Okay, so we're just going to call on our matplot library to plot, and we're going to plot the number of games played, right? That's our num list variable, and our accuracy list. We're going to give that plot a title. I'll call it improvements because hopefully it's going to improve. We'll give it a Y label. And so our Y axis will be our ConvNet accuracy. And plt.x label, we're plotting the accuracy versus number of games played or number of Pokemon drawn. And we can show that plot to the user. All right, and so the final thing we want to do is save our history. Again, using our np.save, we're going to save to our history file, global variable, and we'll save our history data. So that is it. As you can see, we've got less than 170 lines of code. We've defined a neural network, we've been able to interact with the user, and we've been able to have a network that learns from those interactions in less than 200 lines of Python code. And that is what makes this stuff really cool, in my opinion. No complicated logic here, I don't think. Really simple application, but it does something really cool.
In conclusion, thank you for watching our video, and I hope you enjoyed our presentation. Make sure you like, comment, and subscribe to our YouTube channel. But on a more serious note, all code for this project will be made available on GitHub, and the link will be set in the project submission. Thank you, and once again, I hope you enjoyed.